everyone, thanks for coming back for the causal seminar this week. I'm going to be presenting, so I'm normally the one who's bringing in people to present. I figured I'd slot myself in so I could do some self-promotion. So thank you for coming and joining us today. Today I'm going to be talking about causal effect testing under this thing I call interference. And I'm going to be very precise as to what I mean by interference. But it turns out this is going to be kind of an interesting second order thing that we need to care about when we're thinking about causal inference. This is joint work with Guillaume, who was at Stanford. He's now at Citadel. I don't think he's doing this type of thing at Citadel, but I could be wrong. And also Avi Feller, who's at Berkeley, and Panos, who is at Booth, and he will actually be joining us next week for our causal inference seminar. Okay. So this is the title of the talk. It sounds a little bit complicated, but really where we're going to be living for the rest of this talk is in the city of Medellin, Colombia. Okay, so Medellin, Colombia, here I have some maps of it. It's the second largest city in the country of Colombia. Here, this upper left map is just showing kind of where Colombia is situated in South America. It's in the northwestern part. And then Medellin is in kind of the northwestern part of the country. As we go down to the bottom right, what we have is we have kind of a zoom in to the cityscape of the city of Medellin. Okay. So if we think about the city of Medellin, some of you guys might be familiar with Medellin from the Netflix show Narcos. Okay, it used to be the most violent city in the world. Currently, it has a population of about 2.5 million. And if you consider the broader metroplex, it's about 4 million. And back in the 1990s, it actually had a very high murder rate. Okay, it was about 270 murders per 100,000 people. And if you consider Latin America as a whole, it still had a very high murder rate. It was about 40 murders per 100,000 people. Okay, so crime was always a problem in the city of Medellin. Gangs were rampant, and it wasn't just murders, it was also petty crimes. Okay, so carjackings, burglaries, that type of thing. And so back in 2015, the city of Medellin, the National Police, and the Ministry of Defense got together with some social science researchers, and they said, okay, we want to run a particular experiment. Okay. So as I go to the next slide, I want to present what our view of Medellin is going to be for the rest of this talk, and it's a bunch of gray dots. Okay, and so this is actually the city plotted by all of these street segments. Okay, so we have about 37,000 of these street segments, and we can see that the little white circle in kind of the upper left part is actually the mountainous region. We see this white rectangle right here, that's actually the airport. And then the city center itself, so the downtown of the city, is going to just kind of be right in the center of this block. All right. And so these people got together and they wanted to run a particular experiment. All right, and what was this experiment? Well, they wanted to try and figure out how to reduce crime. All right. So what they did was they said, okay, first we'd like to identify a subset of these streets that are crime hotspots. Okay, so these are a subset of units. Okay, about 1,000 out of all of these 37,000 that have very high crime, right? Measured by some crime index. And what they did was they randomly treated a subset of those hotspots with increased police patrolling, okay, during the year 2015. So what happened with this treatment, and they were very careful with compliance to make sure that this actually worked, is they actually increased police patrols on all of these blue streets. And so basically police cars will kind of drive up and down these streets much more frequently than they would at like a baseline level. Okay, so this is my observed treatment. Okay, so you can see now where this is turning into a causal question. We want to actually understand what happened with this treatment. What was its overall effect? Okay, so the outcome we're going to be focusing on for this talk is something I call total crime score. This total crime score is like a crime index. It's basically a weighted average of all the different types of crime that were happening, murders, all the way down to petty thefts, and it was weighted by the roughly the jail sentence. Okay, so that's how they built this crime score. But I just want to note that this is actually a really interesting data set with a lot of other variables and outcomes. One other thing that they did, okay, this group that collaborated on this large-scale RCT was they took surveys of all of these streets. Okay, so they actually walked up to people on these streets and they said, "Hey, how do you perceive the crime on this street? Is this street safe?" Rated on a scale from 1 to 5. So we have survey data, we have crime perception data, and then we also have a lot of interesting covariates. Okay, so for all of these streets, for example, we have how close they were to a church or to a recreation center, and we have all other many other interesting things that we can measure for all of these dots. Yes.
Yeah, good question, David. So where are the outcomes measured? Are they only measured at the hotspots, or are they measured at all the streets?
The outcomes are measured on all of the streets, okay, all 37,000 streets. Okay, so we have crime data for all of our units.
And are they accumulated over like 6 month period or a year?
I believe it's a 6-month period, yeah, but it could be a year as well. But yeah, so we have these outcome measures that are built up for all of the units in my experiment, all of the units in this case being all of these gray dots, right? So about 37,000 of them. Okay, we have this treatment, we have these hotspots. And so the question is, well, what actually happened with this increased police patrols for the 6-month period? Okay, so just to summarize my thoughts here, right, we want to try and get at 2 questions. Yeah.
These are sort of following. So the units are all the dots, but then the treatment assignment is to the hotspots. Those are groups of dots, aren't they? The hotspots?
The hotspots are single dots.
Are single dots.
Yep.
So some of the dots are larger. I guess I'm confused. Maybe I just can't see well.
Yeah. So that's just the plotting thing. Yeah. So some of the dots are just larger, but I'm trying to kind of amplify where the hotspots are. Yes. But yeah, each of these red dots and each of the blue dots are all single individual gray dots.
And so they usually, even though it looks like the red and blue touch each other, they wouldn't really touch each other. There'd be gray dots in between.
Yes, so the red is a subset of the gray, and the blue is a subset of the red. So questions we aim to answer. All right, so there's this kind of obvious question. Let's call it the direct effect question. Did this treatment decrease crime on the streets that were patrolled at a greater frequency? Okay, so that's trying to figure out the direct effect. And then this secondary question, and this might even be a more natural question given the pictures that I've shown you guys, is that, well, were there actually spillovers to neighboring streets, right? So just because I increased police patrols on those blue streets, maybe it was just a case that crime did not decrease, but it just moved to streets nearby, right? So that's how I'm going to be thinking about spillovers in this context, is actually did the crime just move, did it not necessarily decrease, right? Okay, so we'd like to answer both of these, but this talk is largely going to be on the second one. Okay, and since we have a large-scale RCT, we're going to answer these questions through hypothesis testing. Okay, and to be a bit more specific about that, we're going to have a model-free approach. Okay, so we're going to use a randomization method of inference here. Okay, why are we doing that? Well, I'll get into that in a bit more detail. But there are a very small set of assumptions to kind of do this sort of analysis. So let's just set up some notation here, okay? So we're going to define my observed data, and my treatment assignment is going to be binary, okay? So this Z is just going to be a vector of length roughly 37,000. And it's going to tell me whether or not a given street was treated with increased police patrols. All right. And then my y is just going to be my vector of observed outcomes. Okay. We can think of counterfactuals in this setting, and I'm going to use this notation as z prime and y prime. Okay, so z prime, for example, is just going to be another draw from my design. Okay, it's going to be another potential treatment vector that I didn't actually realize in my experiment. And my design, I'm just going to write as this probability distribution here. Okay, so this is a probability of z prime. And this is something that I have access to because I ran an RCT. All right. We've heard about potential outcomes from a lot of the other speakers in this series, right? A potential outcome for a particular street or a particular experimental unit, I, under a particular assignment, z is just going to be a function of z, right? So what was the crime on street I under treatment assignment z? Okay, this is just going to be a function, okay? And the tough part about causal inference is that we actually don't get to see all of these functions for all of my values of z. And so we have to be clever about how we actually identify this thing. But this, for example, could be the total crime score. All right, and let's first assume that we have no interference. All right, so what do I mean by this in the context of my potential outcome function? Well, what I just mean is that, in fact, my potential outcome, okay, my crime for street I only depends on the treatment status for street I. Okay? What are the two types of treatment for street I? It's just, it was either treated with increased police patrols or it was in control, it wasn't treated at all. Okay, so I have two potential outcomes. Okay, so under a no interference assumption, my potential outcome function is only a function of the treatment status of itself. So I only have two potential outcomes. And if I have these two potential outcomes, right, these are my two kind of worlds that I'm trying to compare, that I'm trying to reason with. What type of null hypothesis can I write down? Well, I can try and answer the question, does treatment have an effect at all? This is trying to figure out whether or not there's a direct effect of my treatment. Okay, what is this null hypothesis just written out? Well, if I want to kind of state the boring thing, that the treatment doesn't have an effect at all, what this means is that my potential outcomes are equal for all of my streets. Okay? So for every single one of my streets I, my control potential outcome is equal to my treated potential outcome. Now, why is this useful, and why is this a nice, simple null to start out with? Well, what this says is that since I only have two potential outcomes, my outcome is actually fixed across all possible draws from my experimental design. Another way to say that is all possible randomizations. So how do I actually go about testing this null hypothesis? We have to go all the way back to the 30s and talk about this thing called the Fischer randomization test. Okay? How does a Fischer randomization test work? Right? It's actually a very, very easy thing to talk about. Okay? Step 0 for the Fischer randomization test is you just need to choose a test statistic. Okay? A test statistic is simply a function of my outcome and my treatment. Okay, so it's a function of y and z. We can think of this as a difference in means, for example. The average of my control unit outcome and the average of my treated unit outcome. Okay, that could be one way that I write down this test statistic, a difference in means. Step 1 is just to compute the observed value of the test statistic. Okay, so plug in what my observed y and my observed z is. You get that thing. The second part is where the statistical uncertainty comes in. Okay? And this is the only probability distribution that I'm talking about right now, is my design. What we're going to do is we're going to then repeatedly sample z prime for my design. And for all of those samples, for all of those z primes, I'm just going to recompute my test statistic. In this case, I call this a randomization value of my test statistic, T sub r. Okay, so we have this observed value of my test statistic, and then we have a randomization distribution of my test statistic. And what we do is our final and third step that we all are very familiar with is we just compute a p-value, right? This is just a summary of where my my observed value of my test statistic lies within the randomization distribution. Okay. And those are the steps. This is a Fischer randomization test. Okay. Now, why is this a valid test? Well, in order to show that this is a valid test, I just need to show that under the null, these test statistics have the same distribution. Okay. My randomization value is equal to my observed value in distribution under the null. And I just do that in 2 steps. Okay, so I take my randomization value of my test statistic, t of y prime z prime. That's equal to t of y z prime, because remember, this null hypothesis is what we call a sharp null. So that means that all of my potential outcomes are fixed. They're fixed at my observed. Okay? And so I just substitute in y prime for y, and then the second equals, the second equality is just equal in distribution, because of course z prime and my observed z are drawn from the same distribution, that distribution being my experimental design. So this is a valid procedure. We get valid p-values, and it's very nice and simple, right? Fischer randomization test. Okay, what are some advantages of what I call Fischerian randomization? This is an exact test. Okay, so what I mean by exact in this case is it's valid in finite samples. There are very few assumptions, right? I'm not actually writing down any model for my outcome. Okay. So there's zero notion of a regression model, of a probability distribution for errors. There's no model for y. Okay, and the third advantage that I'm going to note is that it is robust, right? This is actually a rank order test, so I can do all kinds of transformations to y and I'll still get the same answer. Okay. What are a couple disadvantages? Well, and this is a very easy thing to criticize, and a very obvious thing to point out. It often can only test strong uninteresting nulls, right? This is a very strong null where I'm saying that first, I only have 2 potential outcomes, and second, they're equal across randomizations. Okay, so this is a very strong starting point, and it's also difficult to generalize out of sample. Okay, so this is often a big quibble with randomization inferences that, well, okay, we're just working with this finite sample. It's kind of unclear if this actually generalizes to other countries in Latin America and other streets to other populations, right? But with all of this put on the table, what we're going to do, and kind of the first step we're going to take, is we're actually going to try and take Fischer randomization and bring interference into the picture. Okay, this is still has yet to be done, and what we're going to see is that if we can successfully do this, we're going to be able to answer much more interesting questions and test much more interesting null hypotheses. Okay. So that's our goal. Okay, so let's go back to this no interference assumption. Okay, it's kind of our starting point into this Fischerian randomization with interference. Back when we assumed no interference, what that meant is that my potential outcome, yiz, only depends on zi. It only depends on this one scalar binary number, right? The treatment status of myself, of street I. Okay, and so if we think back to the pictures we were looking at the very beginning, where we had this big city of Medellin, we had all these gray dots, they were kind of clustered together. Some of my treatment streets were kind of close to each other. Some of the hot spots were in various clusters. This doesn't really seem like a very realistic assumption. In fact, we might expect the crime on street I to not only depend on the treatment of street I, but also the treatment of maybe the streets that are surrounding it. All right, seems like a plausible thing. Okay, so what I mean in terms of now my potential outcome function is that, and I'm going to use this word exposed. Okay, yiz is actually depends on or is exposed to multiple parts of my treatment vector, not just one. Okay, so we can think of a couple extremes of this, right, and why this problem becomes very hard and why people have often made the Sutpha assumption is that on the one extreme, which we've already discussed, no interference, we only have two potential outcomes. But at the other extreme, okay, when I let my potential outcome function depend on my entire z vector, which is binary, then I have 2 raised to the n potential outcomes. Okay, so this is a very intractable system to work with. We can't really talk about causal effects or causal testing in this very large sense. Okay, so we want to try and be at some kind of middle ground between these two extremes so that we can bring interference into the picture. Okay, so that's the goal. Okay, so the way that we're actually going to bring interference into the picture and kind of be at some kind of middle ground between no interference and max interference is we're going to introduce this concept of exposure functions. Right? What is an exposure function? Treatment exposures. Okay, so for each of my streets, okay, keeping with our crime example, each of my streets, as we previously discussed, is exposed to something more than Zi. Okay? And so let's have a particular function for all of my streets, f sub I, go from 0, 1. Okay, so actually take in the treatment vector, take an A treatment vector, which is binary, and map to some set of possible exposures. Okay, so this will basically tell me for street I, is it a short range spillover, meaning is it a street that is close to a treated street? Is it, say, a medium range spillover, or is it a pure control spillover? When I say pure control, I mean a street that is sufficiently far away from any of my treated streets on the spatial network. Okay. One very important point is that the definition of this lower dimensional summary of my treatment vector, which is what this exposure function is doing, by the way, is it's just summarizing for every single unit my treatment status. Okay. What's going on here, and what's important to note, is that this set E, as well as all of these exposure functions, are going to depend on the scientific question of interest. And often we work with scientific collaborators to try and come up with the best definition of this exposure function as possible. Because, well, why do we care about this? Well, because this is where my spatial network comes into play. Right? This is how we actually define spillovers and how we define interference. Okay? But what's great about this exposure function, and a very key point to make, is that once I have this, right, and once I've kind of bring this in as a part of my analysis, I can now write down all kinds of interesting null hypotheses in terms of it. Okay, so let's see one particular null hypothesis. We're going to focus on this null for the rest of the talk. Right? Here's a question that now incorporates interference. All right, is there a short-range spillover effect? Okay. So what's going on here? Well, what this is saying is that my potential outcomes are fixed for every unit that has an exposure that is either a short-range spillover or a pure control spillover. Okay, so what this is getting at is this is focusing on streets that are either close to treated streets or streets that are really far away from treated streets, and is saying, hey, these potential outcomes are fixed for these two levels of exposure. Okay, and here in the gray box, I've actually just defined what my spillover and my pure control mean. Okay, what is my exposure function? Well, I'm defining a short-range spillover as an untreated street that is within 125 meters of a treated street, and I'm defining a control as also untreated that is 500 meters away. Okay. All right. So this is now a spillover hypothesis that we would like to try and test. Okay. So see, it seems simple enough. We just brought in this new concept of this function, this exposure function, Fi. So the first question that you guys would probably ask is, well, can we use the classical Fischer test again? Okay. Can we use our favorite Fischerian randomization test that has been around for almost 100 years? And if you guys recall the proof that this is a valid test, we see that actually we cannot, right? And so this fails, and we are unable to use a classical Fisher test in this case because I can't say for every single randomization, for every single draw from my design, that my potential outcome, y prime, is equal to y, right? Because what's going on here, well, my null hypothesis that I wrote down, my spillover hypothesis, let's call it that, is only making a statement about 2 out of the 3 potential outcomes. It's only saying that y short and y control are equal. It makes no mention of the situation where a street is in kind of this middle ground, right? In this kind of middle area where it's not far enough away from tree to street to be considered control, and it's not close enough to be considered spillover, okay? So what we say in the randomization inference literature is we say that this is not a sharp null, okay? We can't actually come up with a valid test because we cannot, and I'll say this, I'll state this, we cannot impute my potential outcomes freely under any draw from my experimental design. So the question now becomes, well, is all hope lost, right? We would like to use randomization inference. It's a very simple procedure. We'd like to test these more interesting null hypotheses that are based on exposure functions that incorporate interference. Is there anything we can do? And it turns out there is. And this is, if you look at all of the existing solutions to this problem in literature, what we have to do is we have to now condition our data. And so what I mean by condition is we actually can't focus on all of my experimental units and all of my randomizations. We have to focus on a subset of both such that my null hypothesis is sharp. Okay, so how do we actually come up with now this thing I call a conditional randomization test, okay? So this is where the talk kind of gets a little weird and where we introduce an object that is strange looking but will be very helpful for us. Very helpful from a computational point of view. Okay, so we're going to keep working with this null hypothesis. Y short is equal to y control. Given a null hypothesis, given this thing, and given an assignment from my experimental design, which I have access to because I ran this RCT, we can simply ask the question, well, which of my streets are short-range spillover streets or are control streets? Well, this is just a binary relationship, right? We can just look at the street network. We can say, hey, these streets are streets that are close to my spillover or close to my treated, they're spillovers. These streets are far away, so they're my control. We can do that for every single draw from my design. So the question is, how can we visualize this? Well, this is probably the most important part of the talk. So I'm going to talk about this object I call the null exposure graph. Okay. So how do we visualize this binary relationship, and how do we bring interference into the picture here? Well, let's do this thing where we line up all of my units. Okay, so these are going to be all of my streets. Okay, and I can't graph all 37,000, so I'm going to just put 3 on the slide. Let's put all of our streets as little dots over here on the left. These are all of my experimental units. And then let's put all of my assignments, okay? These are draws from my experimental design on the right, okay? So just to be clear, each of these dots on the left is a street segment. Each of these dots on the right is the full population treatment vector, okay? So this is one draw from my experimental design. The second dot is a second draw. The third dot is another draw. And what we're going to do is we're going to start with my first draw from my experimental design, and we say, hey, that draw from my experimental design expose street 1 to short range spillover status. So we're going to draw an edge. Okay. The second treatment assignment 2, expose street 2 to short range spillover status. Okay. So under the second treatment assignment, just to be very clear, street 2 was close to a treated street. That's what this means, and that's what these colors mean. Street 3, under that second draw from my design, was a pure control. It was far away from all of my treated streets. Okay, so we draw that navy edge from my second treatment assignment to street 3. And we can keep going. We can go down to the third treatment assignment. Okay, this is another z vector. Remember, this is another z prime. And we see that the third treatment assignment exposes street 2 to pure control status and exposes street 3 to spillover status. Okay. And we can keep going. So a couple things to note about this thing. This graph can be completely constructed if you specify a null hypothesis and specify my design, right? I just need draws from my design, and I need a null hypothesis that tells me what type of interference I'm looking at, okay? And each of these edges is simply going to denote that unit I was exposed to the set, either short range spillover or control, under a particular assignment vector J, okay? So this is something that I can just build. This is kind of a funny looking graph, and I actually have colored the edges, so you could call it a colored bipartite graph. Or if you don't care about the colors, this is just a bipartite graph, right? I have a collection of units on the left that are partitioned from a collection of units on the right, and I only have edges connecting the two of them. And I want you guys to notice something. I want you to notice that street 2 and street 3, and here are my assignments 2 and 3. That is a complete subgraph of this bipartite graph. Okay, so what's going on here? What do I mean by complete subgraph? Well, I mean that it is a fully connected subgraph of this bipartite graph. So take those two nodes on the left, take the two nodes on the right. All possible edges that you can draw between those two nodes are there. All right, 4 edges. This is called a biclick. And what I'm going to claim, and what we see, is that if we actually run our test, so if we run our spillover hypothesis, if we test that hypothesis within this biclick, we can actually impute all of my potential outcomes. So the test, to be very specific, conditioning on this biclick is sharp within this set of units and the set of assignments. Okay? So this is how we're going to construct a test for our spillover hypothesis. Is we're just simply going to condition on a biclick of the null exposure graph, and then we're just going to run a test within that biclick. And then that gives us our answer for the test of this null hypothesis, all right? Okay, so how does this test look? This is a test that we call the Biclickbased randomization test. It has 2 inputs, okay? It has the null exposure graph that I showed you guys on the previous slide, okay? And this graph is going to be uniquely defined given my null. Okay, my null can be anything you want. Choose any set of exposure functions, put in any kind of network, and you can get as an output with your design. If you kind of convolve that with your design, you get a null exposure graph. The second input is just my test statistic. Step 1 is going to be decompose my null exposure graph into a set of biclicks. Okay? So we're going to do a biclick decomposition of the null exposure graph. We're basically going to break it up into a bunch of biclicks. And then we're just going to find the biclick that contains my observed assignment. Okay, so if you guys remember, the assignments were on the right-hand side of that biclick. And then we're just going to run our test conditional on that biclick. Okay? And that's it. This is the Biclickbased randomization test. I'll stop right here. What questions do you guys have? I'm sure you have questions. Yeah.
If you go back to that graph, basically like 4 dark blue edges, right? Not 3.
So there are 4 edges. Yeah, if it's short or control, but for the purposes of our test, we actually we aren't really concerned about the balance between the 2 types of exposures. It just the balance will be whatever it is, and then we just are going to condition on.
Yeah, my question is like, you said if those 2 units and the assignment, they must be fully connected. So unit 2 must be connected to both assignment 2 and 3. Or?
Exactly. Yep.
Okay, but like I'm thinking like there should be a dark line between unit 2 and assignment 2, right?
There, so completely forget about the colors,
Okay.
right? So the colors are basically telling me what the balance between these 2 types of exposures are, and that balance is going to basically dictate how powerful the test is. But just simply the fact that that these edges exist between 2 and 2, and 2 and 3, and 3 and 2, and 3 and 3. That's all I need then to actually, if I condition on this biclick, then my null hypothesis is sharp, and then I'm good to go.
Do you do your conditional normalization within within the assignment that you condition?
Yeah. So both, yes. So I'm only focusing on these 2 treatment assignments, and I'm only focusing on these 2 units. So this is conditioning both sides. Yeah, exactly. Yeah.
So when you take the conditioning set, it doesn't include all the units, or it might not include all the units.
Correct.
And so usually I think of like there's a trade-off between like the generalized, like internal and external limit in that movie. So is that presumably comes up here?
Yeah. So that will always be an issue when you're talking about these finite sample tests, for sure. Even if you're running like a classical Fischer test on the direct effect, right? There's a strong argument to be made that, well, this makes sense for these particular units, but I'm not really sure how to make any statement about generalizability. Yes, when here I'm even subsetting my finite sample even further. And so, so when we actually think about interpreting this test, it will for sure be important to see, okay, which units are actually a part of this claim.
Because with the spatial thing, you would have some unit, even across all the randomizations, you'd have some units that are much likely to appear with either colored edge, just by virtue of their relationship, their location over to the other.
Yeah.
Screens.
Yeah. And so you know what? And it's not even clear what that type of pattern should be, right? So given this particular way to condition, you would hope that there would be some kind of like uniformly distributed, like okay, I'm going to pick up like units that are spatially uniform. Some of the other methods, so there's a method that Susan Nathy proposed a couple years ago that basically randomly samples the focal units to try and keep that spatially uniform. But then the issue is that well okay, that's something you can do, and then you can try to find like the click or the set of treatment assignments that they corresponds to that set of randomly sampled units, but that click might be very small. And so then there's this kind of trade-off of finding kind of the biggest conditioning set, but not being like completely agnostic to the network structure.
Looking for this specific application about boundary and so forth, how do you have you done anything to adjust for the spatial confounding? Because I saw I also read the papers, and it looks like a lot of the control units are far apart from city. Maybe there are some other, and when they quite really uniform across all the.
So I mean, since this is an RCT, right? I mean, we're thankfully we don't really have to worry about this type of confounding that comes into, so that's not going to affect the validity of the procedure. It could most definitely affect the power. And so the way that we would try to control for that is actually through the test statistic. So we could, for example, instead of having like a difference in means, so we have all kinds of variables, right, for all of these different street segments. And what we could do is, instead of having a difference in means, it only takes y and z. We can have, some kind of complicated regression function. Pick your favorite one, BCF, BART, whatever, and then have that be your test statistic, where you're actually inputting then also x values, or maybe previous prime values, right? And that could help, and does help actually with the power of the test. Okay, so it kind of sharpens up my statistical inference. Okay. All right, good. So this is kind of the main object of the paper. It's a little funny, but as soon as you kind of get this idea of, well, okay, I have to find a biclick of this object, and I condition on it, then I'm good to go. Then that's basically it. Okay, so here is a proof that this gives a valid method. Okay, this proof is going to be very similar to my classical Fischer randomization test proof. Right, the only thing that I'm going to add here is that, okay, well, I need to condition on this biclick that contains the observed assignment. Okay, so here, what I'm defining is now these click test statistics. So this is basically the test statistic function that is now restricted to units and treatment assignments within my click. And what I need to show is that these two test statistics are equal in distribution, conditional on C, this click. It comes from my click decomposition. And there's really only one or two extra steps here for this proof, right? So we say that, of course, my overall test statistic is equal to my test statistic restricted to the click. And then what's great now is that because I'm conditioning on this click, this complete subgraph of this weird bipartite graph, I can actually impute my potential outcomes under the null. Okay, so y prime of C is equal to y of C. Okay, and then the rest of the proof kind of follows as it normally does. Okay, so this is why this is a valid method. All right. Just wanted to briefly mention a couple related papers. Peter Arno and Susan Afey both have very interesting ways of trying to get at these conditioning sets. Right, when you actually want to bring interference into the picture, you have to be more careful about how you look at your data and how you condition. Both of these procedures, and I kind of mentioned this before, particularly for Susan Afey's approach, is that it's a very general procedure. It works in theory, but there is a massive loss in power, and this loss in power comes in this kind of random selection of focals. When I say focals, I mean street segments. Okay, so basically what she proposes is that you kind of randomly select streets, and then you find the maximum induced click that corresponds to that set of streets. Okay, so in practice, these things are very, very difficult. There's also this fairly recent biometric paper by Guillaume that looks at a very particular experimental design. Okay, it looks at a cluster of interference, and it actually shows that you can, with kind of a careful analysis, you can develop a permutation test that basically gets at this conditioning. Okay, so for particular experimental designs where I have two-stage cluster interference or something like that, you might be able to develop a more powerful test. But the whole point is that in general, and in particular, if I have this crazy spatial network where I have this experiment on this big city and all these city streets, it's very unclear how to condition. Okay, this isn't this nice setup where I have classrooms or households, and then I'm treating a unit in a classroom or a household, for example. Okay, so we wanted to try and develop a completely general framework for this. Right. So let's go back to our map and let's actually look at some pictures now and see how this works in practice. Okay, so we're going to return to our map. This is my observed treatment, my Z-ops. Okay, so we had 967 total hotspots. Those were those red dots. Of that 967, 384 were treated with increased police patrolling. Okay. Just for that particular Z-ops, now I can actually color in light blue, all of the spillover streets. Okay, this is how we build the null exposure graph, right? Take a draw from my experimental design, one draw being my observed treatment, and then just look at and color in my spillover streets. These are the streets that are within a 125-meter radius of my blue dots, okay? And these dots, of course, are bigger just from the plotting than the gray dots, all right? Just to kind of emphasize where they are, okay? And then my second exposure in my null hypothesis is my control exposure. These are streets that are far away from all of my treated streets. Okay, so we can see exactly where those are. These are going to be streets that are at least 500 meters away from any of my blue dots. Okay, and this is for one treatment assignment, my observed treatment assignment. All right? Yes?
Most of those dark blue ones were never eligible for treatment to begin with because they're not hotspots. Is that right?
Yes.
Should I be worried about that?
There's no restriction that you have to have non-zero propensity because so as soon as you write down a spillover hypothesis, you're actually making a statement about all of my units, and your scientific question becomes, well, okay, I'm trying to figure out how crime changes on a particular street, and the treatment is whatever it is. It's not a subset of hotspots, whatever. But the point is that I can now consider my whole network, right? So for sure, some of these streets will always be pure control streets under draws of my design, right? So that's maybe what you're getting at.
But ultimately, what you observe on those streets is going to serve as a stand-in for the unobserved potential outcome in the treated streets. So you're taking a bunch of control units who were never eligible for treatment to begin with for some fundamental reason linked to the fact that crime is not happening. Or they didn't fit whatever definition of hotspot. And then using the crime outcomes. It's more like a. Anyway, you see what I'm saying? Does that make sense?
Yeah. So yes. Yeah. So what I would say is that, and so as soon as you enter into the realm of interference, right, you just because you have an experiment on these hotspots, right, and you have kind of nice statistical variation on these hotspots. All I'm doing is I'm writing down a spillover hypothesis for all of my streets, and I'm making no kind of restriction on how often I expect their status to change or to be flipped. I mean, it could be the case, and you know, for different draws from my design, some of these become spillover. Yeah. Some also don't. Some may always be control, but the point is that as soon as I propagate my design through my exposure function, all bets are off, right? In terms of, you know, having this nice randomization structure, and so I need to somehow capture that, and I capture that with a null exposure graph. And then that's simply how I figure out how to condition, right? It could be like a really crappy test. In fact, it could be a powerless test, right? So I mean, it could be the case that that the click that I condition on only contains control streets. So then I have no way of testing this hypothesis. We'll see that that's not the case, but that's something that could happen. So I'm trying to be as general as possible when I'm thinking about this problem.
Yeah. All right, one last question. What's the name for the other type of exposure?
So the navy I call control, and then the light blue I call spillover.
Yeah, spillover. Is there like an addictive effect for the spillover? For example, I think your definition is analogous as long as this neighboring street has at least one, it's close to at least one treated street, then it has the same spillover. But if that street has like 2 or 3 or multiple treated neighbors within that defined range, is there active effect?
Yes. So what you're proposing is potentially a different type of exposure function, and you can for sure write that down and do the same exact thing. We kind of just treated this as, okay, we're going to define spillover in this way at least one per street, and for sure some of them are going to have like a ton, especially in like within the city center. Right. But that's just how we wrote down this particular exposure function. But what's great about this is that you can, with your scientific collaborators, you can write down any exposure function that you want and still do the same exact thing. So the whole idea is that for draws from my design, we can actually remake this picture over and over and over again, right? We can keep coloring in these dots, either light blue or navy, and the output is going to be our null exposure graph. So let me give you a different view of the null exposure graph, okay? So what I have on this slide, on the vertical axis, I have my treatment assignments, okay? So every single dot, basically I'm plotting 2 matrices here. The left is my null exposure graph, and the right is the click that I condition on, all right? In fact, I'm plotting sub-matrices because I can't actually plot the full null exposure graph for this problem because it's so big, all right? But every single row corresponds to a different population treatment, C prime, and every single column corresponds to a different street. And so we see, right, as my treatment assignment changes, how a given street's treatment exposure changes. Some of these streets are going to be streets that are kind of always in the middle, and so they're not exposed to short or control, but instead they're in this neither category. They're going to be labeled white. The streets that get exposure to spillover are going to be colored light blue, just like they were in a null exposure graph, and the streets that are exposed to control are going to be colored navy. Okay, so we see that some streets are never exposed, some streets are exposed to both, right? Changing colors as we move up and down the columns. And then some streets, of course, are going to be always control, right? These streets, the streets that are kind of solid navy columns, are always going to be and are most likely the outskirts of the city. Okay? And so what we do is with this null exposure graph, we've taken a statistical problem, we've turned it into, here I say a computational one. And our goal is to find a large biclick of this graph, okay, of this thing on the left that contains my observed assignment. And as soon as I find that biclick, I just run my test within it. Okay, so this is my biclick. So what it means, and this biclick is on the right. So what this means is that when I find this biclick, I'm basically trying to remove all of the units and all of the assignments that give me the color white. All right. And so we see now what the variability of my treatment exposures are within this biclick. And I basically just run the test within this, right? So what happens when I apply this to the Medellin data? Okay, well, so the statistics of the null exposure graph, and what we had in our data set was we had a little bit over 37,000 streets. We took 10,000 draws from my experimental design, okay? And those 2 dimensions define the dimensions of this bipartite graph, right? I have 37,000 nodes on the left, 10,000 nodes on the right, and then if I draw all of the edges, I have about 163 million edges. Okay, so one interesting thing that I can look at is the density of this null exposure graph. It turns out the density of this graph is going to be very important for statistical power, right? When I actually think about how sharp or how good this test can be. Okay, and so the density of this is going to be a little above 40. When we find the clique that we want to condition on, what we get is we have about 4,000 of those streets within that clique, and we have about 1,000 assignments. Okay, so my number of focal units is 4,000. My number of focal assignments is roughly 1,000. Right? This is a graph on the left of the city of Medellin, and I'm showing now the observed assignment, the treatment exposures for that observed assignment, and in green, I want you guys to check out where the focal units are. So these are the units that are in the clique that I condition on. Okay? All of these green dots. And what we see is that, well, the focal units generally, we have a lot within the center of the city, and then we have a lot on the outskirts of the city. And this is something that the clique method kind of automatically finds out, is that this pattern is what we need to run our conditional randomization test. And if we were to use a method like ATHES, for example, it would be very, very difficult to come up with a conditioning that would give us that type of pattern. Okay. So once we condition and once we actually compute the p-value, which you know, after all this complicated stuff, what we get to look at is a randomization distribution and a p-value. Okay, so basically the area under the curve up to this blue line, which is my observed test statistic, and we see that this p-value is less than 5%, which tells me that the crime on spillover streets is actually not the same as crime on the control streets, and we can actually invert this test to get an idea of what the magnitude of that effect is, and what we find is that crime on streets surrounding treated streets actually decreases. Okay, and so there is a spillover effect, and what actually happens is that crime is not moving to the spillover streets; it's actually decreasing. Okay, so not too surprising. We have increased police patrols in a given neighborhood. That's actually going to decrease crime in the streets that are surrounding that neighborhood. One other brief thing I would like to mention is that there are all kinds of interesting things that we can start to look at. One of them is actually experimental design under interference. Okay, so when we think about designing an experiment, this is in general a very hard problem, even if I just want to estimate direct effects. When we bring interference into the picture, and when we're talking about RCTs on spatial networks in cities, for example, this is a very difficult problem. But let's say, for example, that I'm interested in testing my spillover hypothesis, right? This thing that we've been looking at throughout the talk. And let's say that my design is simple. Okay, I have one probability for treating the city center, and I have another probability for treating the outskirts of the city, P0 and P1. All right. And the question is, well, what is the optimal P0 and P1? Right? How should my coin be weighted for the center of the city and for the outskirts? Right? And what we can do is, well, we can actually just simulate to figure out what the optimal design is. So here what I have is the vertical axis is P1. Okay, so the probability of treatment for units on the outskirts of the city. And I say outskirts just is defined by a certain radius. P0 is the probability of treatment for units in the center of the city. And we see that we have this nice convex surface, and we have an optimal design space, right? So for a plausible alternative hypothesis, this was actually just under an additive treatment effect hypothesis, which is, if you think about this, this is just a very simple outcome model. Right? So we have a particular outcome model in mind, so we can then get at statistical power. We see that we can actually, through simulation, come up with a nice way to come up with experimental designs. Okay. Here on the right, I want to show you guys the average number of focal units, okay, for the clicks for all of these different designs. And what we see here is that, well, as my probability of treatment goes to 0 for both the city center and for the outskirts, the number of focal units in my conditioning clicks is going to increase. But what's happening is that, and there's this trade-off between the number of focal units and the number of focal assignments. And so we see that, well, okay, we need a click with roughly 600 focal units, but as soon as I try to ask for more and more focal units within my click decomposition, I start to lose my treatment assignments and my conditioning click, and my power starts to degrade. Okay, you see the power starts to degrade as I get closer. Okay, so and this is all in the paper, but there are all of these interesting trade-offs that's going on within this conditioning set. With that, I'll conclude. So presented a new method for testing of causal effects on interference. The whole idea is we wanted to keep this as general as possible and basically propose a new framework and a new way of thinking about interference, and kind of leave all of the knobs up to the statistical analysts and to the scientific collaborators, right? You get to choose your own exposure function. You get to, consider or think about how you define a network. And then as soon as all that's in place, you can use this Biclickbased randomization test to talk about spillover effects for your RCT. Okay. There's all kinds of interesting future work to talk about, some of which we'll hopefully be doing in the Salem Center. And there will hopefully be a lot of work on model-based approaches. So actually bringing in Bayesian models, Bayesian regression models into the picture here to basically help us with power. Because we all know that Bayesian regression models are very useful in this context as well. Thank you guys for coming. Any questions online, please? So I sufficiently confuse people.
But I have a few questions about the treatment in it. How did the treatment in this case work? Were more officers hired? Were officers told to adjust their route to patrol these hotspots more often? Can you just talk more about?
Yeah. So good question. So the baseline level of patrolling on all the streets, first of all, that stayed the same. So officers had to work more to actually patrol these hotspots. And so there was basically an increase in the patrolling intensity for these hotspots. And they would basically, instead of, there was some baseline level of patrolling, and then the hotspots that received treatment, let's say, got maybe 30 minutes more of patrolling per day, is I think what they did. So yeah, and there was no trade-off in the sense that we need more resources, so we're going to kind of take patrols away from other areas. They try to keep everything consistent so that they had kind of the right treatment design.
How granular is the data? So basically, I'm thinking about that showed that the green areas are sort of far away from the city center. The way I'm thinking of this is essentially the street is only treated when an officer is actually patrolling. There's one version where it's only treated when an officer is actually patrolling. And if I wanted to say commit a crime, okay, I wait until the officer's gone. And so it's a terrible question, but I wonder if you have granular enough data, if you can't get more controlled areas, if the patrolling was on some sort of schedule.
Yeah. So I think maybe you're kind of getting at it'd be nice to have some panel data, like maybe some kind of time series variation where Yeah.
Basically, how granular is it? Do you know the times the students are patrolled, or?
Yeah, so with the current data that we have, no. So yeah, these things are kind of aggregated up over time. But yeah, that would be a very nice feature to have. And yeah, I think your point is well taken. It'd be interesting to try and target that treatment even further and figure out exactly when these crimes are being committed relative to the patrolling. But we don't have that currently.
The last thing you talked about when you had the different probability assignment, remind me what the two different probability assignments correspond to?
Yeah. So basically so we wanted to try and figure out if we could come up with an optimal experimental design. This could be made a very complicated problem, so we wanted to try and keep it simple, and so we said, all right, let's have a probability of treatment for the city center as its own thing, as its own scalar between 0 and 1. Let's have a probability of treatment on the outskirts, something different. And okay, what are the optimal values of these parameters? Optimal in the sense of we have large statistical power for testing the spillover hypothesis. And as soon as you write down an outcome model, this power is something that you can just simulate and calculate. And so we just did that, and this is what we found.
Yeah. So I guess, it seems perfectly reasonable to say I'm going to define outskirt and city center and have two probabilities to get a handle on this. But I'm just sort of curious your thoughts on whether it would make sense to extend that type of idea. So instead of having this binary city center or outskirts, you could have the assignment probability be some other function of like the degree. It's not really the degree of the node, it's the spatial network, but like something else about the density of the other streets relative to the next street. So if you wanted to say, I want to treat more dense areas of the city more or less.
Yeah.
Is this the type of thing that seems reasonable to explore?
Yes. Yeah. I completely agree. I think if you actually want to design an experiment, taking into account like network density, like how, these are things that we can easily get from our spatial network, right? Because we have our streets, we have the streets that are connected to the other streets, or they're close or whatever. We have clusters and stuff. So taking more measures or more characteristics of the network into account, I think would be really cool. And and that's definitely something that I'd like to work on for sure.
In the US at least, they have data on like transportation patterns across the city, right? So you get some other notion of connectedness.
That's right.
Geographic proximity would be cool.
Yeah, completely agree. Cool. All right.